Hello, thanks for tuning into the video. This is our last lesson of the semester. We're looking at lesson 5.5, solving logarithmic equations. Might not be the last video of the semester, might make some review videos. We'll see what happens, but definitely our last lesson of the semester, and then we're looking at final exam review from here on out. To start us off, let me do a little bit of a throwback here with some previous knowledge that we need to remember. Well, it's one of our log properties that we need to remember. If you recall, log base b of a to the y, we can rewrite this. This was in the last lesson. We can rewrite this as y times log base b of a. The exponent can be brought down like so. We definitely need to know that, all right? So, as we're looking at these equations, let's take a look at where the variable is. Where is x? We're trying to solve for x, and take a peek. X is in the exponent for all of these, right? That's different. That's new. How do I solve for x when it's in the exponent? Well, let's just look at this problem and feel good about it and think about what is similar to the things that we've already done, not just in my class but in years past, right? What is something that we all fully have an understanding of? We all understand we need to get x on its own, right? We gotta get x on its own. We have to solve for x. We need to get rid of the 3. We need to get rid of the 2 and the 5, right? We just want x equals, right? But how, right? How do we get x on its own when it's stuck up there in the exponent? Well, that's why I just reminded us of this property right here. We can bring down an exponent when there's a logarithm involved. So when you solve these equations, and honestly, I'm going to refer to these as exponential equations. When you solve exponential equations, you're going to be using a log every single time. So take a look at this first problem, 3x to the 10. Well, you know when we solve problems, right? We can divide 2 to each side. We can add 3 to each side. We can take the square root of each side. Well, guess what? We can take the log of both sides. And that's exactly what I'm going to do. So I just took the log of both sides. Why? Because now I can use this property right here. The next step here, I'm going to bring down the x. X times log of 3 equals log of 10. And then to get x on its own, I can simply divide, let me write it out. I can divide by log of 3 to each side, because this is x times log 3. So to get rid of it, I'm going to divide. And whatever I do to one side, I of course do to the other side. And my final answer here is log 10 of log divided by log 3. We could also get an approximate decimal for this simply by plugging it into our calculator. But just for the sake of time, I'm not going to pull up and tediously plug it into a calculator, right? We've got our final answer right there, okay? Maybe I'll do 1 or 2 with a decimal. Let's check it out again, okay? Take a look at this problem. What do you notice that's different about this problem compared to the other one, right? Pause for dramatic effect, pause the video if you'd like. What do you notice that's different? There's this plus 5 that's involved, right? Well, just like any other equation, right? If I'm trying to get x on its own, right, get rid of what you can, right? So how do I get rid of a 5? A plus 5, I'm going to subtract by 5. And then at this stage in the game, how do I get rid of the 2? You don't really get rid of it per se, right? What really needs to be done at this point, right? This is essentially the same point in time, right? If x is stuck up here in the exponent, I need to take the log of each side. Why am I doing that? Because once again, because of this property, it allows me to take this x and bring it down. So I have x times log of 2 equals log of 7. And then I can divide by log of 2 to each side, because this is x times log 2, so I divide by log of 2 to get rid of it. And I now have x equals log of 7 divided by log of 2. And again, you can just plop that straight into a calculator. We're getting a little bit spicier here, so to speak, because there's a little more than just x. There's just a little bit more than x in our exponent, but nonetheless, I'm still going to attack these problems the same way. Try to get x on its own, get rid of what I can. Well, I'm pretty sure we're all fairly certain that if I have a minus 3, I can simply add 3 to get rid of that. 4 plus 3 is 7. And then now I'm at this point where all I have is the exponent, right? 3 to the 2x. You can't divide away the 3. I know there are some students that they're like, oh, what do I do? Like, I either multiply, divide, add, subtract. They've got that stuck in their brain. No, you don't cancel out the 3. We have to be creative here, and we take the log of each side. And this creativity allows us to bring down the exponent. So we have 2x times log of 3 equals log of 7. So the thing that's different here is to get x on its own, this is 2 times log 3, but this is also 2 times x. So I need to divide by 2 and log 3. So dividing by 2 cancels out the 2, and dividing by log 3 cancels out the log 3. Whatever I do to one side, I do to the other, of course. And voila. There's my answer. Now, honestly, this is a moment where, you know what, let's plug it into our calculator just once, just to make sure. I want you to be able, I need you to be careful about how you're plugging this in, right? Depending on what calculator you're using, Desmos is obviously like our go-to friend here, right? Because it displays it very nicely. If you're just using a regular calculator, you got to be careful about your order of operations, right? When you divide the 2, where are your parentheses, right? I'd encourage you to use Desmos, and you can plainly see here. And I'll go ahead and write that down. 0.88. That 6 would round that up to that 5 up to a 6 as well. So 0.886. There we go. Let me skip around to one more. I think you're getting the point. Let me just do one more, right? Let me do one more. Let's take a look at the one with E, right? That might kind of throw you for the loop. That might kind of scare you. Remember, E is just a number, okay? So in reality, it's no different than the problem that we just did, to be perfectly honest, right? It's no different than the problem that we just did, because E is just a number. Imagine it's a 2 for all I care, right? We're going to treat it the exact same way. So we have 3e to the 5x. Well, I have this exponent right here, right? How am I going to get x out of the exponent? Just jump straight into it. Log of 3e to the 5x times log or equals log of 14. I took the log of each side. That allows me to bring down the 5x. Again, this creativity that we're using here, the why are we using the log, right? Really think about that. Why are we using a logarithm? Because that's what allows us to bring down the exponent. How could we do that any other way, right? This log property is what seals the deal for us. If we weren't using the log, we'd never be able to get that x out from out of there, right? It's trapped. So to get x on its own, divide by 5 and log of 3e. Divide by 5 and log of 3e. Whatever you do to one side, you do to the other. Cancels, cancels, x equals log of 14 divided by 5 times log of 3e. Pretty straightforward, right? We're only 10 minutes through here, right? I encourage you in the comments, if you're watching this, I encourage you to do this. Let's think a little bit. In the comments, describe the steps to solving in your own words. Okay? Is there a pattern that you notice? Right? Is there something that I didn't say that you're noticing? Right? Is there a way that you can put it in a nutshell for me? I'd appreciate it. So what's a why? Right? Well, why do we need to know this? Right? What's a good use case for this? Well, when solving word problems that deal with growth or decay, being able to solve with logarithms is like quite a big deal here. Okay, so do you remember these problems? Right? Because we've seen these. We solved them in a kind of inaccurate way, and maybe not inaccurate. It was more of an estimate. It was more of an estimate, and here we can really get to the nitty gritty here. So recall, right, that every single one of these equations is written like this: total equals start times your growth rate slash decay rate raised to the t. An initial population of 900 frogs decreases at a rate of 14% per year. Set up an exponential equation and solve it to find when it will be worth half its original value. So our starting number of frogs is 900. We are decaying or decreasing by 14%. Well, 1 minus 0.14 is 0.86. This is us decaying by 14%, right? 14% as a decimal is 0.14. So we're going down by 14, 0.14. And when will the number of frogs be half? Well, half of 900 is 450. So the question is, how many years need to pass in order for our frogs to have this value? Well, if our variable is up in the exponent, what do? We can take the log of both sides. Something that I kind of notice here, though, that this is 900 times 0.86. How about I just clean it up just a little bit, right? Because that's just 900 times, right? It's kind of separate. So I can just divide that away. And 450 divided by 900, well, that's simply a half, or 0.5. Now that looks a little bit cleaner. I hope you're with me on that, right? You wouldn't have to do that, but I just think it kind of cleans it up a little bit. Take the log of each side. I say again, why are we doing this? What is the point of taking the log? What's the advantage? Because that's the only way that this gets to get brought down, right? And therefore, t is log of 0.5 divided by log of 0.86. And I'll plug that into a calculator for us. Log of 0.5 divided by log of 0.86 So after about 4.6 years. 4.6 years. That's an okay answer with me. Is that an okay answer with you? After about 4.6 years. So there's a big reason why we want to be able to solve these equations. And this could be anything. I've brought this up in the past before, right? Okay, it's not the number of frogs, but it's the value of your money in a savings account, and it's growing. It has 14% growth. Now you wouldn't get that in a savings account, of course, maybe your stocks or something like that, right? But when will my investment reach this value? When will my whatever, right? You could predict lots of things using this very simple structure. All right, so let's kind of turn it on its head just a little bit and look at these log equations. So now we don't have exponential equations, we have logarithmic equations. Let's do a little star again, some previous knowledge here. This is from a couple lessons back when we first introduced the logarithm. When we take the log of a, we get an answer. Let's call it x. Well, we can rewrite a logarithm in exponential form. And I've said this on repeat a couple times. The base of the logarithm becomes the base of the exponent. And then the a and the x, the two numbers, switch sides. Boom. So I can rewrite this logarithmic expression into an exponential expression. The base of the log becomes the base of the exponent, and these guys switch sides. Boom. So take a look at the first one. You might be thinking, where's the base? What's the base? Remember, a naked log, a log without a base, is the common log, which is log base 10. Okay? So even think about like square root. We don't write square root like that, right? We write it like this. Okay? So now we rewrite. Now we rewrite because instead of the compare and contrast, instead of the variable being stuck in the exponent, instead of the variable being stuck in the exponent, it's now stuck inside the logarithm. How do we break it free? By rewriting. The base of the log becomes the base of the exponent, and these guys switch sides. Whoa, I just solved for x. There it is. Your multiple choice option maybe on Canvas might be a fraction though, because remember, 10 squared is 100, but 10 to the negative 2 is 1 over 100. Negative exponents force us to take the reciprocal. Okay, forces us to flip. Let's do it again. There's a little more going on here, right? There's a little more going on, and I'm like, okay, if I were to rewrite this, what do I have too much going on, right? So again, do what I believe in you, right? I totally believe in you. Do what you know how to do, right? Do the things that you know, right? How do you get rid of -3? You add 3, right? That's almost probably instinctual for a lot of us, right? Don't second guess yourself, okay? Get rid of the stuff that you're like, just get this out of my way. Get out of my way. Exactly. Get it out of the way, right? What's the natural log? It's a log with a base of e. There's that number again, right? And we rewrite, right? Because the x is stuck inside this log. When we rewrite, the base of the log becomes the base of the exponent, and these guys switch sides. Oh, x is just e to the 8th, which that's a pretty big number. I just punched it into a calculator. It is 2,980.958. Now, these first two were pretty easy and straightforward, but let's look at the directions. Solve the equation, check for extraneous solutions. We've heard that word before, extraneous. Extraneous means fake, kind of, right? It's like a teaser. It's a fake answer. It's like you think it's right, but it's not right. It's this mysterious fake answer. Sometimes it won't work. All right. Sometimes the answers that we get won't work, and I'll show you when and why that happens. But I guess I'll say it now. The reason why, I'll show you when it happens, but the reason why is because you can't take the log of a negative number. I mean, try, right? I mean, you try to. You can't. You can't take the log of a negative number, undefined. You cannot take the log of anything negative. It's impossible. So basically, anytime you get a negative, you ought to be on high alert. Okay. Let's do it again. Log of 4x plus 1 equals 3. Get rid of this stuff, right? We don't want it. Bye-bye. This is a naked log, so there's a little 10 there that we can't see. The base of the log becomes the base of the exponent, and these guys switch sides. So 100 equals 4x. Oh, just divide away the 4. X is 25. No worries about that being extraneous. I mean, you can just imagine plugging this back in, right? 4 times 25 is 100. Oh, that's positive, right? No worries. Let's go again. Get rid of this, right? If you'll notice, right, I'm isolating the logarithm every time, right? I need the log on its own before I can rewrite. You know what I mean? Like I don't have extra stuff here, right? I don't have extra stuff around here as I'm solving, right? It's just log. So you need to isolate the logarithm by getting rid of the 3. You need to isolate the logarithm by getting rid of the 1. You need to isolate the logarithm by getting rid of the 5. The base of the log becomes the base of the exponent, and these guys switch sides. X is 11. You can try plugging it back in real quick. 11 minus 2, oh, that's 9. That's positive. No worries, not extraneous. All right, a few more. And at this point, folks, if you're watching, right, or you are watching me and you feel like you've got it down, you could almost dip out at this point. But there's just more examples here, right? You haven't seen extraneous solutions, so maybe I spoke too soon. I've got the problems done out here. You can't see it. Let me get you one that's extraneous. So spoiler alert, this one's going to be extraneous. And, well, wait a minute. Maybe I definitely spoke too soon. This one looks different because I have logs on both sides. What's up with that? Well, do you remember? Man, I'm doing lots of recalling, right? Previous knowledge things. Do you remember these problems where we had the same base of the exponent? And I said whenever the base of the exponent is the same, they essentially kind of cancel each other out, and all we have to focus on is the exponents. Well, the same thing can be said here, right? The same thing can be said here. If my logarithms are the same, well then in reality, all I really care about is the inside. That makes I think that makes logical sense, right? If part of the equation is already the same, what we care about is the part of the equation that's different. Okay? So, boom, set those equal. And solve. Now, I said this was extraneous, and let's see why. Well, I got x equals negative 5. Now, I said be on high alert. So we plug it back in. 2 times negative 5 is negative 10. Plus 1 is negative 9. I can't take a log of negative 9. Negative 5 minus 4 is negative 9. I can't take a log of negative 9. I can't take the log of negative 9. This is not going to work, okay? Let's take a look. This one looks messy, eh? This one looks interesting. What do you think we're going to do here? I'd love you to think about that, and maybe pause and think about this. What do you think we're going to do here? Well, this is another property that we've seen before, right? Adding logarithms means that you can multiply their insides together, right? So let's multiply these two guys together. Be careful. Let's do our little box technique. X plus 2 times x minus 3. X squared, 2x, negative 3x, and negative 6. That comes out to be x squared minus x minus 6. So I can combine these logarithms to form this equation right here. Now I have one log on one side, one log on the other. They're the same, log and log. It's the exact same thing that I just did for G. Set the insides equal to each other. Don't hate me. It's a quadratic equation. It's a quadratic equation. Oh no, right? Set it equal to 0, factor and solve. Come on, we've done it a million times. Don't hate me. Set it equal to 0, factor it up. You end up with x minus 7, x plus 5. Remember, the question that we're asking ourselves is, what multiplies the negative 35 and adds to negative 2? Negative 7 times 5 is negative 35, and negative 7 plus 5 is negative 2. So our two solutions are 7 and negative 5. So I can take these and plug them in to check them. 7 plus 2 is 9. 7 minus 3 is 4. 7 plus 29 is 35. We're good. Negative 5. Negative 5 plus 2 is negative 3. Negative 5 minus 3 is negative 8. Negative 5 plus 29 is positive 24. But these guys are both negative. So this is an extraneous solution. X is only 7. There's a lot of examples here. The video's getting a little long. I'm going to go ahead and power through the rest of these examples, but you've seen it all at this point, right? You've seen it all. If you're feeling comfortable, great. You can go ahead and get started on the classwork ahead of time if you'd like. If you'd like to see a couple more examples, I'm just going to go ahead and finish it out, okay? A log on both sides, set it equal. Set the insides equal, right? Imagine it was 2 to the 3x plus 2 equals 2 to the 2x minus 1. Lots of us were getting these problems right on the classwork, right? If the base is the same, they just kind of cancel out. Well, if the log is the same, they just kind of cancel out. And solve. But I mean, I told you, right? Anytime you see a negative, you got to be on high alert. You plug that in up here. 3 times negative 3 is negative 9. Negative 9 plus 2 is negative 7. No solution. Right? And this one down here was no solution. I forgot to say that. Or I forgot to write that. I said it was extraneous, but I forgot to write no solution. All right, last but not least, we got natural log. No different though. Don't be afraid of the log, of what type of log it is, because in the end we just treat them all the same anyways, right? If you see two logs adding, you can multiply the insides together, right? That's what we did up here. Okay. We multiply those insides together, and then why am I spacing what to do? Oh, I didn't really multiply them, right? Let me I just kind of wrote it out. I don't know what I was thinking there, right? X times x is x squared, and x times -2 is -2x. And then, interestingly enough, I can rewrite this, right? This is log base e. This is log base e. So let's do it. Because I don't have a log on both sides. You realize that, right? You might have been tempted to be like x squared minus 2x equals 0. No, because I don't have a log on both sides, right? I don't have a log on both sides. That was what I could do if there was a log on both sides. So now I have to rewrite. So this is e to the 0 equals x squared minus 2x. Anything to the 0 is 1. Set it equal to 0 and solve, because take a look at this. We have another quadratic equation. Spacing the word there. And what a shame. We're gonna have to use the quadratic formula, right? This isn't factorable. Man, Mr. Whitefoot isn't treating us nicely here with our notes today. So A is 1, B is -2, C is -1. So negative b plus or minus the square root of b squared minus 4ac all over 2a. I'm going to run out of room. So 2 plus or minus the square root of the two negatives here are going to cancel. That becomes a positive 4. And this negative is going to cancel when we square it. So that's plus or minus 8 all over 2. Let's just leave it like that. Although, is one of these... Sorry, the video's ending with me being a little sluggish here. You know what? Let me be awesome and pull something up for you. Let's pull it up on Desmos. Honestly, I'm getting stressed by the algebra. You feel me? I'm getting stressed by that. So I have the function x squared minus 2x minus 1. So where does it touch the x-axis? Here and here, right? So those are my two solutions. This is -0 or negative 0.414. So that's negative, right? You with me on that? Let's call it -1/2. Let's call it -1/2. Well, if I plug in -1/2 into this guy or this guy, I'm going to have a negative. So only the positive half. Only the positive half. Negative is extremes. All right. Sorry to get that hectic problem at the end. I don't even think a single problem on the classwork is that difficult. But you know what? It's nice to see that challenge like that. So if you watched it this far, you're an incredible human being. I thank you for watching. I appreciate you. Good luck on the classwork. I'll see you in class. Bye. Au revoir. It's been real. All right, see ya.